Yo, I'm back. Things seem to be running a lot smoother after I restarted. I also grabbed some food, so I'm excited. I'm excited to get back into stereochemistry.
We've got the hydrogen at the back, and then this side of the ring is different from that side of the ring. We've got a tertiary carbon here versus a secondary one on this case. This carbon has the carbon on one side, the amine group on the other, a hydrogen, and then also this tertiary carbon at the bottom. And then the bottom carbon, similarly, has a hydrogen attached, a tertiary carbon up top, a quaternary carbon to the right, and a secondary carbon to the left. So all of the circled atoms here are chiral centers. Now, the last thing that you should be able to quickly calculate once you've identified how many chiral centers the substance has is how many different possible stereoisomers the substance has. And that is calculated by raising 2 to the power of the number of chiral centers in the molecule. So if we look at substance 2, we know that 2 to the 2 would be 4. And in this case, 2 to the 3 is 8. So the cyclic structure on the right has 7 different molecules, 7 different isomers, where each of these 3 chiral centers are in a slightly different orientation. Now finally, when we think about what it means for something to be chiral, compounds have this physical property called optical activity. And what that means is that they are able to rotate plane polarized light. So a couple of symbols that you likely to come across in reference to chiral compounds are either D and L, which are lowercase italicized letters that stand for dextrorotatory and levorotatory, which just means that the light is rotated in either clockwise or counterclockwise orientation. And you might also see this plus and minus. So plus is associated with dextrorotatory. Minuses is associated with levorotatory. So you can't look at a structure and know whether the substance is going to rotate plane polarized light in the clockwise or in the counterclockwise way. This is something that has to be measured with a piece of equipment called a polarimeter. And we don't really have a good understanding of how a particular chiral center translates to whether the plane polarized light is rotated clockwise or counterclockwise, or even to what degree the rotation occurs. So this has to be experimentally determined. But otherwise, all chiral compounds will be optically active. So as a summary, what we talked about in this video was the definition of chirality, how to look at a molecule and identify whether it is chiral or not by finding chiral centers. And we also briefly reviewed what it means for a substance to be optically active. In this video, we'll be discussing the basic reactivity of the carbonyl functional group, as well as a specific type of reactivity known as tautomerism. Now, to rationalize the main type of reactivity of the carbonyl experiences in solution, I want us to think a little bit about resonance. So if I were to localize the electrons of the carbon-oxygen pi bond up onto the oxygen, I could draw a resonance structure that looks like this. In reality, for this molecule, is an average of these two representations, such that I'll have some partial double bond character between the carbon and the oxygen, but also some partial negative charge on the oxygen. It's a partial positive charge on the carbon. And this is the important reactivity that we're going to focus on. The other reason that I can sort of justify that this carbon has some partial positive charge is that oxygen and carbon have different electronegativities. So when we think about the polarity of that bond, we would expect the more electronegative element to hold on to the electrons more tightly, thereby giving the carbonyl carbon an electron deficiency, so a partial positive charge. So what we find is that the carbonyl carbon is electrophilic in this functional group. Now the other thing that we should consider is that whenever I have a hydrogen on an alpha position to the carbonyl, this hydrogen will be acidic. Because if I were to deprotonate that hydrogen, I would leave behind the negative charge, and that can be resonance stabilized because of this adjacent pi bond. So let's focus a little bit more on this alpha hydrogen acidity and talk about this idea of tautomerism. Now, if I were to deprotonate any alpha hydrogen of an aldehyde, or thing that we should consider is that whenever I have a hydrogen on an alpha position to the carbonyl, this hydrogen will be acidic. Because if I were to deprotonate that hydrogen, I would leave behind the negative charge, and that can be resonance stabilized because of this adjacent pi bond. So let's focus a little bit more on this alpha hydrogen acidity and talk about this idea of tautomerism. Now, if I were to deprotonate any alpha hydrogen of an aldehyde, or a ketone, using some sort of base in solution, then I'd get a structure that looks like this. So I already mentioned that. I can resonance stabilize this negative charge, so let's draw what that structure would look like as well. And either representation of this reactive species could be referred to as an enolate. Now, when I think about reality for this molecule, remember that it's an average of these two resonance structures. So what I'm going to find is that an enolate behaves something like this, where I have some partial double bond character across this 3-atom system, and some partial negative charge on both the oxygen and the terminal carbon of this 3-atom system. Now, when I think about the relative stabilities of these two resonance structures, you should hopefully conclude that the structure at the bottom is the more stable resonance structure, because the more electronegative element is shown with a negative formal charge. Now, when we start to reprotonate this anion now, I've got two places where I've got some negative charge, so it could pick up the proton. So if I were to add the proton back to the carbon end, we just go back to the aldehyde or the ketone that we started with. And this is referred to as the keto form of the molecule. If, however, I were to reprotonate back at the oxygen end of the enolate, then I get a structure that looks like this. Looks like an alcohol connected directly to an alkene. And so this thing is referred to as the enroll form of the compound. So if you think about where the hydrogen should go, we've got two options for nucleophilic or basic ends. And remember that what determines a better base or a better nucleophile is, again, relative electronegativity. So because oxygen is more electronegative, it can better stabilize this negative charge, whereas the carbon, which is less electronegative, can't stabilize it as well. And therefore, this is the more reactive end of the enolate molecule. So while you're more likely to see an enolate drawn in this resonance structure, you need to remember that this is the business end of the molecule. So it's much more likely that you're going to protonate down here at the carbon end and maintain this strong carbon-oxygen double bond, rather than protonate up here at the oxygen and get a slightly weaker carbon-carbon double bond. So what that means is that if I were to deprotonate an aldehyde or a ketone, I could form a small percentage of the anil in solution. But for the most part, these two structures are going to exist in equilibrium, and that equilibrium heavily lies toward the keto end. Now, if I think about the isomeric relationship between a keto form of an aldehyde or a ketone and enol form, how are these things related? Well, they all have the same numbers of atoms of each different type of element. However, the atom connectivity is different. We've moved that hydrogen from a carbon to an oxygen. So if I think about what the isomeric relationship is here, these things are structural isomers. So this equilibration between the keto and the enol tautomers is referred to as tautomerism. And so our strict definition here would be the rapid equilibration of structural isomers. Now, the last thing what I want to throw into the mix, when we think about this tautomerism and alpha carbon acidity, or alpha hydrogen acidity, is that MCAT often asks about this idea of incorporation of a deuterium atom into a molecule, or deuterium exchange. So anytime you've got any acidic kind of hydrogen in a molecule, anything that's as acidic or more acidic than an alpha hydrogen, you can deprotonate it with base, and then let that sit in a solution of D2O instead of H2O. And the deuterium from the D2O will be the proton donor and replace the hydrogens with a deuterium atom. So you might see a question on the MCAT asking you about a molecule like this. How many equivalents of deuterium can be exchanged for any hydrogens in this molecule? And the answer here would be 6, because you've got a methyl group on each side. Each methyl group has 3 acidic hydrogens. So be on the lookout for this idea of deuterium exchange on the MCAT. So as a summary, we focused on the segment, the relatives, the activity of the carbonyl functional group, mostly being electrophilic at the carbon of the carbonyl, and seeing that alpha hydrogens to the carbonyl are acidic. We looked at tautomerization being the rapid equilibration of structural isomers, the keto and the enol form, and saw that the keto form is much more stable. And we also looked at the reactivity of the enolate, and saw that the carbon end of the enolate is the most reactive end of the molecule.
Some karam curry.
In this video, we'll be discussing imines and animines. Now, an imine is a functional group that has a carbon-nitrogen double bond. and they form when a primary amine, so a nitrogen that is sp3 hybridized with just one carbon group attached, which is what makes it primary, acts a nucleophile and attacks the carbon of a carbonyl compound, so an aldehyde or a ketone. Now, an amino group is not quite as good of a nucleophile as something like a hydride reducing agent or an organometallic reagent, so we're going to run this reaction under acid-catalyzed conditions, which means that all the mechanistic steps are reversible, similar to hemiacetal and acetyl formation. Now, the details of the mechanism are not really important for the MCAT, but it is important that you can recognize the difference in these functional groups, in that you know that a primary amine is responsible for making him imine, and that water is going to be a byproduct. Now, the other thing that you'll note is that even though the first thing that happens in this mechanism is that nitrogen, with its lone pair of electrons, acts as a nucleophile and does an attack onto the carbonyl. Like all other nucleophilic addition reactions, it's not a true addition, or it's not simply an addition because we end up making a new pi bond at the end. So this process actually has an addition as one of the first steps, but also an elimination step that happens a little bit later in order to reform that pi bond now to the nitrogen instead. Now animines are similar to imines, and the mechanism by which they occur is pretty much identical up until the very last step. And animines form when we use a secondary amine as the nucleophile. So now this nitrogen has two carbon groups attached to it, which is what makes it secondary. So again, without going through all of the mechanistic detail, the next to last species along my reaction pathway looks something like this. And I might call this an iminium ion. And when the iminium ion is formed, in order to get rid of that positive charge,
The food was really spicy. Oh, hey, don't take it up. I didn't, I didn't know. It's just like we had family prayer, so they trapped me pretty much, and I forgot to put the transition thing. That would have been nice, but it is what it is.
Charge. There's no acid catalyst that I can regenerate easily by just sort of deprotonating the carbonyl or deprotonating the imine A like we could in the previous reaction. And so, instead we're going to have to do is let the byproduct water pull off a hydrogen alpha to the carbon-nitrogen double bond. So the last step here is going to look something like this, where we'll push these electrons out onto the nitrogen to sort of neutralize that positive charge. In the anamine is actually this functional group right here, where we have an alkene with a mine group directly attached to it. So this should be very similar to another functional group called the anal that you should be familiar with, where an OH group, that would be an alcohol attached to an alkene. Now we have an anamine. Now, again, notice this is done under acid-catalyzed conditions, so all of these steps are reversible. Now, the other thing that I want to draw to your attention is another way that the anamine can react, because I've got a carbon-carbon double bond, and this nitrogen has a lone pair of electrons. Anamines are actually relatively electron-rich and therefore can behave as nucleophiles, similar to an enolate can be a nucleophile. So if I were to push the electrons on this nitrogen out in this general direction toward the alpha carbon, and I had a willing partner for this nucleophile, some sort of electrophile that could accept the electrons here, and kick out a good leaving group like iodide, then what I can do is add, or alcoholate, alpha to the anamine. So in the same way that enolates can behave as nucleophiles, my anamines can behave that same way. And this is actually, the formation of an anamine is one way that we can make a carbonyl compound into a relatively good nucleophile in the absence of deprotonating it and making the enolate directly. So we've alcoholated alpha to the anamine, and now, because this is now that same iminium ion, if I treat under acid-catalyzed aqueous conditions, I can take this molecule and revert it back to the original aldehyde or ketone now, with the extra carbon booth at that alpha position out here. So to summarize, we see that imines and anamines can form reversibly under acid-catalyzed conditions, with the imine being formed from a primary amine, and an anamine being formed from a secondary amine. And that the anamine is nucleophilic at the carbon alpha to the carbonyl, and once it's alcoholated can be reverted back to the original aldehyde or ketone under those acid-catalyzed conditions. Of electrophile that could accept the electrons here and kick out a good leaving group like iodide, then what I can do is add, or alcoholate, alpha to the anamine. So in the same way that enolates can behave as nucleophiles, my anamines can behave that same way. And this is actually, the formation of an anamine is one way that we can make a carbonyl compound into a relatively good nucleophile in the absence of deprotonating it and making the enolate directly. So we've alcoholated alpha to the anamine, and now, because this is now that same iminium ion, if I treat under acid-catalyzed aqueous conditions, I can take this molecule and revert it back to the original aldehyde or ketone now, with the extra carbon booth at that alpha position out here. So to summarize, we see that imines and anamines can form reversibly under acid-catalyzed conditions, with the imine being formed from a primary amine, and an anamine being formed from a secondary amine. And that the anamine is nucleophilic at the carbon alpha to the carbonyl, and once it's alcoholated can be reverted back to the original aldehyde or ketone under those acid-catalyzed conditions. We'll be discussing the properties and reactivity of the carboxylic acids. Now, in addition to the obvious type of reactivity of carboxylic acids being reasonably good proton donors, or acids, you should also keep track of a couple of other types of reactivity and properties. So from a physical perspective, carboxylic acids are polar molecules. And that high polarity gives rise to larger melting points and larger boiling points because these things can hydrogen bond, as indicated by this structure. So not only is the carboxylic acid group of hydrogen bond donor because of the OH group, but it can also accept hydrogen bonds because of the lone pairs of electrons on either of the two oxygens of the functional group. So these kinds of ideas might come into play when you're thinking about separation techniques on the test. Secondly, one of the main types of reactivities for the carboxylic acid, they can be reduced to primary alcohol if I use a strong enough reducing agent. So whereas aldehydes and ketones can use a weaker reducing agent, like sodium borohydride, carboxylic acids need to use a strong reducing agent, like lithium aluminum hydride, with the subsequent acidic workup step to get me my primary alcohol. Finally, if I want to make a derivative of carboxylic acid, then we have to go through sort of a nucleophilic addition elimination kind of reaction, where in a very general type of sense, we'll have some sort of nucleophile attack, the carbonyl carbon, kick some electrons up onto the oxygen of the carboxylic acid in an addition step, because we're breaking the pi bond. We'll make some sort of tetrahedral intermediate that will then reform the carbon-oxygen pi bond, kick out each group, which depending on the kind of reaction we're doing, might end up being protonated under acid-catalyzed conditions to make a better leaving group since hydroxide isn't a very good leaving group. And we'll do an elimination. Elimination is something we recognize because we reform the carbon-oxygen pi bond. And so effectively, we can see that we've done what looks like a substitution. We've replaced the OH group of the carboxylic acid for whatever this incoming nucleophile is that gives us some new carboxylic acid derivatives. So, to summarize this video, we see that carboxylic acids are highly polar. Good hydrogen bonders have high melting points and boiling points. They are also at a very high oxidation level. So we're going to need a strong reducing agent to convert them into primary alcohols. And carboxylic acids can be converted into several types of derivatives, and the process through which this occurs is an addition elimination mechanism. Now when we think nucleophile is not, that means I don't have a great, I just think solution that may be present adjacent to the In this video, we'll be discussing how to convert carboxylic acids into their derivatives, as well as do a general review of a lot of carbonyl chemistry. Most carboxylic acid derivatives can be generated directly from the carboxylic acid. Acid halides are one of the derivatives that can only be generated from the acid itself. It cannot be generated from another carboxylic acid derivative, because acid halide is the most reactive of all of them. So in order to do this reaction, we'll treat the carboxylic acid with either a Cl2 cyanyl chloride or PCl3, if we want to make the acid chloride, or PBr33 if we want to make acid bromide. Acid anhydrides, as the name suggests, are two carboxylic acids that have been condensed and had water removed. So anhydrous means without water, so we usually heat these reactions up. We remove water as it's being formed, and by an audible principle, we can favor the formation of the anhydride. Esters are formed from the carboxylic acid, and whichever alcohol we want to attach by treating
Wait, this is a crazy revelation. It's not someone sitting behind a desk writing these up. It's an actual person speaking, and they transcribe the voice memo and then feed it into a voice gen. That's crazy. That's crazy. Yo. But it makes so much sense. It's not like a super savvy writer like sitting there like trying to make the robot sound as real as possible. It's oh, yo, yo.
under acid catalyzed conditions. And the final derivative of the carboxylic acid is called the amide. And these things cannot be made from carboxylic acid directly, because the carboxylic acid is acidic. The nucleophile we would need to make an amide would be an amine. And what we see instead is a proton transfer between the acidic carboxylic acid and the basic amino group. So if I want to make an amide, I have to first convert the carboxylic acid into one of these three derivatives, and treat one of these things with the amino group to make the amide. Now when we think about carbonyl chemistry in general, I want to ask some big picture kinds of questions here. And the first is, how do we know what kind of nucleophilic reaction is going to apply if I'm looking at a given starting material? How do you know what happens when the MCAT throws some starting molecules at you? Well, the first thing you should do is find the carbon-oxygen pi bond. If we're going to do a nucleophilic addition, it's always going to happen because that carbon of the carbonyl is electrophilic, either because of a resonance justification or because of polarity. It will be electron deficient. So the next thing we'll be looking for is, what kind of electrophile do I actually have? If the electrophile is not that great, can we still do the nucleophilic addition? And the answer is yes, as long as the nucleophile is pretty good. And if the nucleophile is not that great, if the nucleophile is weak, then how do we make the reaction go instead? Well, there's two different things that we can do. We can either make the electrophile a better electrophile, and usually we do that under acid-catalyzed conditions. Adding a proton onto the oxygen of the carbonyl gives it a positive charge, and therefore that carbon is more electrophilic. The other thing that we can do is we can make the nucleophile better, and usually we do that by deprotonating the nucleophile. So if I wanted my aldehyde or my ketone to be the nucleophile itself, I could make this into a better nucleophile by deprotonating alpha here to make an inaudible. Now the other thing that might happen in these nucleophilic addition reactions is, sometimes we see elimination happens after addition. So does that happen always? Well, only if I've got a good leaving group, so something electronegative next door to the carbon of the carbonyl. And if I don't have a leaving group, then what we're going to do instead is we're going to take that 0-, and we're going to protonate it via some acid workup steps. We will make an alcohol as the product instead. So when you think about all of carbonyl chemistry, there's really only 4 different kinds of things that could happen in their reactions. We're either going to do a nucleophilic addition, and sometimes be able to do an elimination. And if we need to activate our electrophile, we can protonate. If we want to activate our nucleophile, we can deprotonate. And then at the end of the reaction, if we had a good nucleophile to start with, and the nuclear condition happens first, then we'll protonate at the end to make an alcohol as we just described here. So if you think about this, we can review a couple of different kinds of reactions by just thinking about these 4 different steps. So if I were to protonate, meaning I don't have a really good nucleophile, so I'm going to activate my electrophile, then I let the nucleophilic addition occur, and then I deprotonate. Well, then that could be something like making an acetyl. Another option could be deprotonation first, meaning I don't have a great nucleophile, and I want to make it a better one. We get the nucleophilic addition to occur, and then we protonate the alkoxide at the end. That might be something like an aldol reaction. Another possibility might be to do a nucleophilic addition, and then a protonation, which means we already have a good nucleophile present. And then we're just going to protonate at the end, which means we don't have a good leaving group. So that might be something like hydride reduction or maybe a Grignard reaction to make an alcohol. Finally, I could have all 4 of these things happen, so if I do protonation at the beginning, that means I don't have a great nucleophile. I'm going to activate my electrophile. I will allow the addition to occur, and then an elimination, and then we'll deprotonate at the end. So this looks like acid-catalyzed conditions to make some sort of carboxylic acid derivatives, most likely an ester. So you can see that lots of different types of reactions, making lots of different types of products, are all done under the same combination of 2 to 4 of these possible steps. So when you're trying to think about predicting products for carbonyl reactions on the NCAP, don't worry too much about memorizing lots of details. The point of this slide was not to say memorize which combination of all these things is going to give you which compound out here. The point is to say all carbonyl reactions are going to have very common, very familiar types of steps in them. And in order to think through how the reaction might possibly occur, or a reaction that maybe you've never seen before, that you might have to deduce what's going to happen here, you should look to see whether you've got a good nucleophile, a good electrophile, whether you've got the potential of a leaving group in order to be able to predict what might happen. So to summarize the video, we saw that most carboxylic acid derivatives, all but the amide, can be synthesized directly from the carboxylic acid. And remember that the acid chloride can only be synthesized from carboxylic acid and not from any other derivatives. We also looked at the carbonyl functional group as being pretty consistent in the way that it reacts, and our need to assess whether I have a good nucleophile or a good electrophile, and whether there is a leaving group present adjacent to the carbonyl, to be able to predict what kind of reaction might occur on the MCAT.
expect to be any good. Okay, yo. Much time left? Okay, yo, eat. Okay, eat. Yo. Yo, what? Those trends because it's got phenol, bro. Ah, phenol, bro. That glazed right over my head. Ah, shoot. See y'all later. I'm tired. Bye. I'm actually not that tired, but I need to go to sleep. I have